Hello everyone. There has been some confusion on what's being asked for in discussion board number 4. So I'm going to post this video today and it's going to go through everything step by step. You're asked to take the numbers, the two columns of numbers that are in the Excel file that are attached to the discussion board and calculate the range, the standard deviation, both biased and unbiased, and the variance. And in the variance case, you can post the biased and unbiased variance as well. So I am going to show you exactly how to do that. First of all, I think most people will get the range part. The range is just the range of numbers, and you get a range value by subtracting the smallest value in your set from the largest value. For the column of height, your largest value is 87 and your smallest is 44. So you just do that subtraction and that will be your range value. The same with weight. Your highest value is 173, your lowest is 114. Do that subtraction and you will get a single value, and those will be the ranges for the height set and the weight set. The second part asks you to calculate biased and unbiased standard deviation. And it's unfortunate that they're using the term biased and unbiased because I think it's unnecessarily technical, and I can explain it in a better way. First of all, standard deviation is the average difference from the mean. So if you have a set of numbers and you calculate the mean by taking all of the numbers, adding them up, and dividing them by the number of numbers that you have, you will get the mean value. What you then do is you calculate how much each number deviates from the mean, and you essentially calculate a mean of that deviance, and that's your standard deviation. So really what the standard deviation tells us is how far is any data point in the set likely to be from the mean, because again, it's a calculation of the mean difference. An unbiased standard deviation is used for samples, and that's an important distinguishing factor. It's used so that samples are more conservative, and the sample standard deviation is a bit of an overstatement of the true standard deviation of the population. Well, what does that mean? Okay, what does it mean to be more conservative? Remember that when we take a sample, we are taking a snapshot of something that looks like our population, but it is not our population. So we can't technically calculate a mean, a standard deviation, or even a variance for the population using the sample that is going to be 100% correct. There will always be some error in there. So that is why we used what's called unbiased standard deviation, because when we do unbiased standard deviation, we are correcting for the error so that we sort of overstate the error, so that when we actually try to apply anything we learned about the sample to the population, the error is corrected for, so that we're just a little higher. So we're on the safe side. We're taking the safe side. And that, unfortunately, is called the unbiased standard deviation. A biased standard deviation is used for the entire population, and that is when you have the whole population, have access to the whole population. Maybe your population of numbers is only 100 numbers long, and it's easier to get access to them. We don't need to be conservative because we are not inferring anything. We are looking directly at the entire population. So when we calculate the standard deviation, we're calculating the actual standard deviation for the entire population. That's the difference between unbiased and biased. Now, how does that work? Well, let's look at the process. For calculating standard deviation, first thing we do is we calculate the mean. All right, so we have 20 numbers in our sets. Calculate the mean of those 20 numbers. The next thing we do is we take that mean and we subtract it from every one of the 20 values in our data point, or in our data set. And that's going to give us some negative numbers, and it's going to give us some positive numbers, because the mean is going to be higher than some and lower than others. If we were to just average those and say that that's the standard deviation, we're going to be in trouble, because what will happen is the negative numbers will cancel out the positive numbers, and we'll wind up with something pretty close to zero. Now, in some statistical tests, that's a useful test in order to be able to sort of calculate the amount of error that you have, but in our example, it's not useful, and we don't want to do that. So to get away from the zero issue and the positives and negatives canceling each other out, we will take every single one of our 20 values, the positives and the negatives, and we will square them. Because a positive times a positive is a positive, and a negative times a negative is also a positive. So everything becomes positive. So now we have 20 positive values, and they're the squares of the differences between each of our 20 data points and the mean. Then we add all of those up, and that gives us a great big value. Okay. And here's where the unbiased or the biased part comes in. After we've added up all those squares, the sum of the squares, we want to calculate the average of the sum of the squares. When we're doing an unbiased estimate of the standard deviation of the sample, we divide by n minus 1. In our case, n is 20. So we divide by n minus 1, or we divide by 19. If we want a biased estimate of the standard deviation of the population, maybe 20 is our entire population, then we simply divide by n, which would be a straight average. So we'd be taking the sum of the squares and we'd be dividing it by the number of numbers we had, which is 20, and so the sum of the squares by 20 would give us our straight average. But what happens when we take the n of 20 and we subtract 1 to get it down to 19? That's going to be dividing by less than 20. Thus, the value that we get is going to be slightly higher than the value we would get if we divided by n. So if we want an unbiased estimate of the standard deviation of the sample, we divide by n minus 1. Because using the sample to calculate the standard deviation is an estimate, and we want to be conservative in our estimate. So we take away 1 from n to make our estimate more conservative. And here's an example here. Assuming that my n is 10, if I were to divide 100 by 10, I get 10. But if I drop n by 1 down to 9, divide 100 by 9, I get 11.1. It's slightly higher error, slightly higher standard deviation, but again, it's allowing me to be more conservative because I am inferring the population standard deviation based on my sample. If we want a biased estimate of the standard deviation of the population, we divide by n. In this case, we would do the 100 divided by 10 equals 10. Again, we are not estimating for the population because we have the entire population. There's no need to estimate or infer. So there's no need to be conservative, and we get the real value for the standard deviation. So part 3 here is how do we calculate variance? Well, I've actually already told you how to calculate variance. We calculate the sum of the squares. That's, remember, we take the mean, subtract it from each one of our data points, square that value, and add up all those squares. And that's calculating what's called the sum of the squares. We divide that by n minus 1 if we're using a sample, and we divide it by n if we're using the entire population. And that gives us our variance. The variance is the sum of the squares divided by n minus 1 for sample, and the sum of the squares divided by n for the variance. But there's one step more. Remember, we squared all of those differences, and we added those up, and we took the average of those, but we're still dealing with squares, things that have been squared. And so s squared is actually equal to our variance. But if we want to get s, or our standard deviation, we have to take the square root of it. So that's the last step to get us to the standard deviation. We have to take the square root of the variance. So the square root of the sum of the squares divided by n minus 1 is the standard deviation of the sample. And taking the square root of the sum of the squares for the whole population divided by n will be the standard deviation of the population. How does this look in Excel? Now that I've told you kind of the mechanics behind this, you really can always use Excel to calculate this. So when you go into Excel and you do standard deviation function, use a standard deviation function, you'll find that there are two of them. One of them is .s and the other one is .p. Standard deviation .s is the unbiased calculation of the standard deviation using a sample. And it works like this. Equals stdev.s, and then you, in parentheses, put your numerical range. The standard deviation.p is the biased calculation of the standard deviation for the whole population. And it just, the difference is this is n minus 1 and this is n. The variance.s is the unbiased calculation of the variance using the sample. And the function is equals var.s, and then you put your data range in there. And the variance p is the biased calculation of the average of the variance using the whole population. And I didn't put the function in there, but that would just be equal sign var.p. The same difference exists here. When we're calculating the variance for the sample, we use n minus 1. When we're calculating the variance for the population, we use n. I'm going to take you now to Excel. Assuming I can get there. Yeah, here we are. And show you this in our data set. And I used height. These are the values are sorted. No, they're not sorted. Yes, they are. They're sorted by weight. Anyway, it's the same values that you have in your data file. If you come down here and you look, I have put in equals var.s. That's variance for the sample. A2 to A21, and that's what is in my range there, A2 colon A21. Remember the equal sign, otherwise it will think you're typing text. And this becomes a function to calculate the variance for my sample. And the variance for my sample is 130.78 if you're rounding. I do the same thing for the variance for my population. The variance for my population, var.p, in my parens, A2 colon A21, and it gives me a variance of 124.24. This is my unbiased, and this is my biased. This is my n-1, and this is my n. And that's why this one is higher than this one, because this one assumes you're looking at the entire population. The same thing works for standard deviation. With my standard deviation function equals stdev.s for sample, I have A2 to A21, and I get a standard deviation of 11.4, basically 11.44. If I do the standard deviation for the population, I get equal standard deviation.p, A2 to A21, and I'll get a standard deviation of 11.14, that was probably 11.15. That is my bias standard deviation. Remember, this is the sample, I divided by n-1. This is the population, I divide by n. And that's really the difference between biased and unbiased. It's whether or not you're dividing by n-1 or by n. I will let you know that as your number of data points gets larger, if you're dealing with 500 data points or something like that, the differences between the sample population and the sample standard deviation and the population standard deviation become very, very small. And that's just because we're getting closer in the number of records to something that looks like a population. Even if the population is much larger, the more records we get, the more likely the differences between those numbers are going to be very small. If you have any further questions, don't hesitate to contact me. I'm happy to help you with more answers.